Welcome to this explainer. Today, we're taking standard science revision and turning it into a high-stakes look at the invisible, honestly kind of dangerous force powering your everyday life. We all plug things in every single day without a second thought, right? But behind those plastic wall sockets lies a fascinating battle of physics. So let's strip away the casing and look at exactly what's happening inside the walls of your home.
Here's our roadmap for mastering household electricity so you can nail those top-tier grades. We're covering 1. Decoding the UK main supply, 2. The anatomy of the 3-pin plug, 3. The dangers of live devices, and 4. Fuses and earth wires. Let's dive in. Section 1. Decoding the UK main supply.
Okay, first things first, we absolutely have to distinguish between the direct current powering your phone battery and the alternating current surging out of your wall socket. Direct current, or DC, is super straightforward. Just imagine electrons marching in a single, orderly line in one direction only. That's battery power. But the mains electricity in your home? Entirely different beast. It uses alternating current, or AC. In an AC circuit, the potential difference is periodically reversing its polarity, bouncing between positive and negative, which forces the current to continuously change direction. And why do we use this for mains electricity? Because it works seamlessly with transformers, allowing us to step up voltage and minimize energy losses heat across the national grid. It's a total game changer. Now, you might be wondering, just how much push does this alternating current actually have? Well, the UK main supply operates at a high potential difference of 230 volts. This is a critical number you absolutely must memorize for your exams. Think of voltage, or potential difference, as the electrical pressure literally shoving those electrons along. 230 volts is a tremendous amount of pressure, vastly more powerful than the tiny 1.5 volts you'd get in a standard AA battery. And here's a top-tier grade 8 or 9 detail for you. 230 volts is actually the effective potential difference. The real peak voltage spikes closer to 325 volts, but 230 is the essential working number you'll use in your exam calculations for heavy-duty appliances. On top of that, this alternating current changes direction with a frequency of exactly 50 hertz. That means it completes 50 full cycles every single second. If you remember your equations, specifically time period equals 1 divided by frequency, that means one complete cycle takes just 0.02 seconds. It is incredibly fast. So remember these two golden tickets, 230 volts and 50 hertz. Moving right along to Section 2, Anatomy of the 3-pin plug. Let's organize the chaos going on inside a standard UK plug. First up, we've got the live wire, which is always wrapped in brown insulation. This is the one bringing the highly dangerous 230 volts directly into the appliance. Next, we have the neutral wire, encased in blue plastic, and it sits at 0 volts. Finally, we have the earth wire, easily spotted by its green and yellow stripes, which also sits safely at 0 volts. Knowing these colors and their exact voltages is completely non-negotiable for understanding household circuitry. To really cement this advanced understanding, let's break down what each wire is actually doing. The live wire delivers the energy, carrying that alternating potential difference straight from the main supply. But electricity needs a complete path to flow, right? It needs a way in and a way out. That's where the neutral wire comes in. It completes the circuit. So the brown live wire is your high potential in, and the blue neutral wire is your 0 potential out. And what about that green and yellow earth wire? It just sits there securely at 0 volts, acting strictly as an emergency escape route. Under normal, safe circumstances, absolutely 0 current flows through the earth wire. Which brings us to Section 3, Dangers of Live Devices. Let's tackle a classic high-level physics trap. Why can a device plugged into the mains still deliver a fatal shock, even if the switch is totally in the off position? You'd naturally think flipping a switch to off makes an appliance perfectly safe to open up or tinker with, right? Nope. That's a super dangerous misconception, and examiners absolutely love to test you on it. The key to answering this lies in the definition of potential difference. Remember, the live wire inside the plug is constantly held at a potential of 230 volts. Even if the switch inside the appliance is open, meaning the circuit's broken and the appliance isn't running, that live wire leading all the way up to the switch is still very much live. Now your body, you're standing there at 0 volts. If you accidentally touch that exposed live wire, you instantly create a massive potential difference between the wire and the earth beneath your feet. Your 0-volt body just became the ultimate direct path to the ground. Because of that massive 230-volt difference and the relatively low resistance of a human body, Ohm's law dictates that a large, fatal current will instantly flow right through you to the earth.
Finally, Section 4, Fuses and earth wires.
To stop that terrifying electrocution scenario, engineers built in some brilliant safety features. The first line of defense is the fuse. You've got to be able to instantly recognize and draw its circuit symbol, a simple rectangle with a straight line running directly through the center. Don't confuse it with a standard resistor, which is just an empty box. That line running straight through represents a literal, very thin piece of wire inside the fuse, and it is intentionally designed to be the weakest link in your electrical chain. For maximum safety, a fuse has to be rated just slightly above the normal operating current of whatever appliance it's in.
Let's walk through the exact steps of how this handles a serious fault. Step 1. Imagine an old washing machine vibrating heavily over time. Inside, the brown live wire frays and makes direct contact with the metal casing of the machine. Usually, touching that casing would mean instant electrocution. But step 2, that metal casing is wired directly to our hero, the earth wire. Because the earth wire has an extraordinarily low resistance compared to a human body, a massive surge of current violently rushes down it instead of you. Step 3, thanks to the heating effect of this sudden, massive current, that thin little wire inside the fuse instantly overheats. Step 4, the fuse melts, physically snapping the circuit in half. This cuts off the life supply, isolating the appliance entirely, and preventing anyone from getting shocked. And the craziest part? This entire sequence happens in a fraction of a second.
So as we wrap up this explainer, I want to leave you with a thought to carry into your exams, and honestly, your daily life. Household electricity isn't just some boring list of wire colors you have to memorize. It's a remarkably engineered, highly reactive system designed to continuously tame a lethal force. From that alternating current shifting 50 times every single second to the sacrificial fuse standing by, ready to melt in an instant to save your life, it really is a masterpiece of physics in action. Thank you so much for joining me to decode the anatomy of power. Keep these principles in mind, and I promise you won't just pass this topic, you are going to completely master it.